This meeting is being recorded.
In this next section of chapter 14, we'll take a look at how concentration specifically can affect rate. So you're told here that we can gain some information about the rate of a reaction by seeing how the rate changes with changes in concentration of reactants. So that's implied that if we were to change the reactants, specifically, we could increase or decrease effect rate in some fashion. So what we see down here in this table is a number of experiments, 6 here, and there are some initial concentrations given for ammonium and our nitrite ions here. And we see this reaction can progress at different rates. So these are our observed initial rates of these different combinations of concentrations of reactants. So the general rate equation that we're going to take a look at in this section is going to have this form where we're going to have rate equals some constant K, and then say this was reactant A, this was reactant B for this specific example. We have the concentration of A raised to some exponent, some power that I'm going to say M here. And then we're going to have the concentration of reactant B raised to another exponent, which I'll differentiate as N here. So for this specific problem here, say we wanted to find how rate is affected by a change in the concentration of reactant A, I could use equations 1 and 2 down here because I'm changing the concentration of reactant A, but I'm keeping the concentration of reactant B constant. So I know that there's no change in B, so that cannot be affecting any change that I see in my rate. So a way to equate these values would be to set, let's see here, we could set rate 2 and divide it by rate 1. We'll set them equal to that equation that I have up there. So some constant K, which will be the same since it's the same reaction. And I'm going to place my higher values on top because that allows for much easier math to calculate M. And then notice we're going to have, oh, that's 0.02. And then this is 0.01, 00. Raised to the same exponent. And then if we were to fill in the concentration of NO2, it would just cancel out here. So we'd have 0.200 and then divided by the same 0.200 raised to the exponent n. So that will just cancel out as 1 because they're the same value. And then we would set these equal to our rate. So I'm going to rewrite it over here. So we have rate 2, again, would be on top, 10.8 times 10 to the negative 7 divided by 5.4 times 10 to the negative 7. And again, we would set that equal to our concentration, 0.02, the higher one, over 0.01 raised to the m. So notice since our exponents are the same, we can do some quick math and see that this divided by this, 10.8 divided by 5.4 will give us 2. And that's equal to 2 as well if we divide 0.02 by 2. So 2 to the m power over here. And the only way to get an answer of 2 is if our m exponent was equal to 1 here. So we can see that by doubling the concentration, we double our rate. So that would be a first order relationship or a one-to-one relationship with the increase in concentration for reactant A. And again, this would be that generalized rate equation shown down here for this reaction. And we could generate a rate law if we were to solve for the relationship between the other reactant. So let's do that also. right now. So we've already solved for the relationship between the rate and our first reactant. Let's choose some equations here to relate reactant B to our rate change here. So again, we want to hold a constant now. So I'm going to choose reactions 4 and 5 here. And we can see if we did that, we could take the rate of 5 divided by the rate of 4, and that would be 21.6 to the negative 7, 10.8 to the negative 7. And again, reactant A is held constant, so this over top of itself would cancel out and just turn into 1. Well, we can't forget our K's that will also cancel out because they're the same, because it's the same reaction. And then we can relate our concentration of reaction 5 for reactant B here, 0.0404 raised to the n, and then this would be 0.0202, again, raised to the same exponent. So what we notice is that the relationship is also going to give us a one-to-one correlation here. So over here, 21.6 divided by 10.8 gives us 2. And then we can set that equal to 0.0404 divided by 0.202. That will give us exactly 2. 2 to the n. We solve for our exponent n. So overall, if we go down here and we fill in for the rate law of this rate equation, the rate law here would be that rate equals K, and then our first reactant times our second reactant here. And that's what we see over here. So there's both first order relationships here, so we do not have to include the exponent or the m and the n that we solved for, since they're 1. So we'll continue in the next video, and we'll solve sample exercises 4 and 5.